Hi friends, we are still in chapter 0 and we're looking at section 011, simple probability and odds. We have a few vocabulary words to keep in mind. Probability is knowing, basic probability is really trying to figure out the ratio between sorry about that, let's do it again. The ratio of the desired outcome to all possible outcomes. Okay, so that's always going to be a ratio. That ratio is going to be somewhere between anywhere from 0 to 1. This means it will never occur. This means it will definitely occur. So anywhere in between 0 and 1, you can have a probabilistic ratio. Let's look at the next one, sample space. Sample space just refers to all possible outcomes, all right? So sample space is everything that can occur. Equally likely is when things are equally likely to occur. Let's say I had a die, a single die, which I have one here, right? Equally likely, if I were to roll this die, if it's a legal die, it's equally likely that I can get any number from 1 to 6. So that's what equally likely means. A tree diagram refers to when you have several different things and you're trying to count all the possibility. So for instance, this is a typical one. If you've got 3 flavors of ice cream and 2 types of cones and 2 types of toppings, a tree diagram would look like, so let's say those 3 flavors of ice cream are strawberry, chocolate, and vanilla, right? So those are the 3 flavors that you could choose, but then for each of those flavors, you could choose 2 different types of cone. You could choose sugar cone, or you could choose waffle, sugar, or waffle. You guys get the idea. And then you can choose your toppings. It could be gummy bears, sprinkles. Let's say gummy bears or sprinkles. I don't know why you would put gummy bears on top of ice cream, but whatever. Okay, so you got gummy bears or sprinkles, and I would do that for each of these. And doing that lets me know just all the possible paths, all the possible choices. So this is a helpful way for counting all possibilities. Odds. The word odds really refers to the ratio. Now, this is different from probability. The ratio of the thing that you want to happen against all the ways it can't happen. Okay? So it's not against all possible outcomes. It's against all the other outcomes. And I'm going to write that down. Let me get rid of this. So that's tree diagram, if you need to copy that down. But when we talk about odds, we are talking about the ratio of the desired outcome to, in a way, the undesired outcome. Not all possible outcomes, but the undesired outcome, the opposite of what you want to happen. So I'm going to do undesired outcome. Okay. Complements. So complements really kind of relates to the concept of odds because complements, well, let me give you an example. So if I have my die again, right? So here's my die, and I know that the probability of getting an even number, because how many even numbers would be here? 2, 4, and 6. That's 3, so that's 3 out of 6 possibilities would be 3 out of 6. Right? So that is one ratio, or 1 out of 2. The complement to that would be the probability of getting the other thing, in this case the odd numbers, and that's going to be 3 out of 6. And when I add those together, I get 1. So complements have to add up to 1. It has to be the probability of one thing with the probability of the other thing, or in some cases like the undesired thing. Does that kind of make sense? Let me know if it doesn't, but these are the vocabulary words that you're going to see in the assignment. So let's get started looking at some examples. So the first example we have is you're going to find the probability of rolling a 1 or a 5. A 1 or a 5. So when I'm looking for this probability, I'm going to write it this way. I don't know why this isn't doing what I needed to do. Aha. All right, let's try one more time, chavalitos, for us. We shall get it together. All right, so here it is. The probability of getting a 1 or the probability of getting a 5. Since we want 1 or 5, we don't care which one, when we roll a die, we're going to add up the probabilities of both. So I know that the probability of getting a 1, again, with a 6-sided die, that's legal, it will be 1 out of 6. The probability of getting a 5 is similarly 1 side out of 6. So I'm going to do 1 out of 6. And when I add that together, the probability of getting a 1 out of 5, a 1 or a 5 is going to be 2/6. And of course, I can reduce this ratio to be 1/3. So you've got 1/3 of a probability of either rolling a 1 or a 5. Let's take a look at some other ones. What's the probability of rolling an even number? Well, we kind of talked about that before. Let's kind of look at this. So probability of rolling an even number is going to be, well, what's the how many different possible outcomes can we have that are desired? So to roll an even number, we'd have to roll 2, 4, or 6. So there are 3 ways to do that, 2, 4, or 6. The probability of the possibilities that are all included would be 6. So that would be 3 out of 6. And so that's all possible outcomes. This is desired outcomes. And finally, we can reduce that to 1/2. And we knew that from before. Let's look at example 2. Example 2, there's a bowl containing 5 red chips, 7 blue chips, 6 yellow chips, and 10 green chips. 1 chip is randomly drawn. Find the probability of each. So the probability of blue would be, remember we have to do, I'm going to do probability of blue is going to be desired outcome, which is blue in this case, desired, I can spell, I promise, desired outcome over all possible outcomes, right? And so the desired outcome is blue. How many different ways can we get blue? It looks like 7 since there's 7 blue chips. So we're going to put a 7 right here. And then we've got to figure out how many chips we have all together. So that's 5 and 7, which is 12, plus 6, which is 18, plus 10 more, which is 28. So 7 out of 28. Of course, I can reduce this and it becomes 1/4. So you have 1/4 of a chance of pulling blue out of this in this particular situation. How about red or yellow? So the probability of red or yellow is going to be given as, well, how many different red or yellow chips do we have? So I look, we've got 5 red chips and we have 6 yellow chips. So that's 11. And that's going to be 11 out of the total number, which we've already calculated is 28. 11 and 28 do not have any common factors, so this is as low as we can go. So that's what we got. What's the probability of pulling no green? No green whatsoever. Now here's an interesting thing. If I found the probability of green, right, I can then subtract it from 1, and that will be the probability of no green. Think about this. The complement to no green would be green. And remember, the complements, when you add up the complements, the probability of each complement, you need to get 1. So if it's easier for me to figure out the probability of green, which it is kind of, right? Watch this. 10 greens. So let me write that nicer. Be a nice teacher and write it nice. There we go. All right, so if I were to calculate the probability of green, I know this is not the answer to the question because it said the probability of no green, but if I found out the probability of green is 10 out of 28, which can be reduced, in this because there's 10 chips, 28 possibilities, which can be reduced to 5 out of 14, I can subtract this from 1 to get the complement, which is the probability of no green, all right? So I'm going to do it this way, which I know seems a little convoluted, and then we're going to talk about the other way to do it. So the probability of no green is going to be 1 minus 5 over 14. And when I do something like that, I'm looking at 1 as 14 over 14, 5 over 14, subtract, we get 9 over 14. So the probability of no green is 9 out of 14. Okay, we can also, by the way, write decimal versions of these types of answers as well. And you guys know how to convert a fraction into a decimal. And if you don't, at the very least, you can pull up a calculator. But you should know how to do that. All right, so how could we have done this another way? Well, quite frankly, we could have counted up all the other things. And so we have all the other possibilities aside from green. So 5 and 7 plus 6 gives me 18. So I would have gotten 18 out of all possible 28, and that reduces to 9 over 14. Both are fine, just utilizing what options we have here just so you can see how we can do it. Let's take a look at another one. So here's example 3. We're going to do a tree diagram here, I believe. Okay, so here's examples 3. I'm going to do it in a tree diagram form. I started doing it and I started saying some silly things, so I had to rewind a little bit. So let me go back and get started. So what we have is we have 2 t-shirt colors, and they could be either maroon or white. And we have a couple of logos that we could put on. We could put on the GSFS logo, Hawks, or a picture of our school. That little picture of the schoolhouse, very cute. Okay, so I'm going to use G for the GSFS logo, H for the Hawks logo, and picture, P for picture, okay? So that's true in either color. And I know you guys calculated this 2 minutes ago, but this is what a tree diagram looks like. So my choices are either maroon or white, and then I can choose each of these logos to put on the front. And obviously that's 6 different choices. An easier way would be to multiply all of the, no, not 6, but 3. 2 times 3 to multiply all of the possible situations that could occur, right? So I could have either 2 of these and 3 of these, and that's basically the fundamental counting principle of mathematics. That sounds really nice. Or you can do a tree diagram so you can get the visual to see it. Sometimes, like let's say there was another variable that we could have added, like, and this t-shirt comes in sizes small, medium, large, and extra large. Then we could have branched off, not with that big marker, but we could have branched off with each of these logos and start saying, okay, well, we've got 4 sizes, and then that would have multiplied by 4 the number of different types of t-shirts that we could get. All right. Our final example, and I'm not going to do a tree diagram here, we'll use the fundamental counting principle, is we're going to think through some ice cream. So here's the situation. An ice cream shop offers 1, 2, or 3 scoops of ice cream. So you've got the number of scoops. Then the scoops of ice cream among 12 different flavors. So then you've got the 12 different flavors. It can be served in waffle cone, sugar cone, or cup. How many possible choices can be ordered? Now this problem seems really simple, and I think the intention, I copied it out of the textbook, I think the intention is to basically have you consider basically multiplying these things together, right? But then the more I thought about it, the more I thought, well, can't you mix the ice creams, right? Couldn't you have a scoop of vanilla, like I don't know what the 12 flavors are, but a scoop of vanilla, a scoop of chocolate, a scoop of strawberry. Can't you have a scoop of strawberry at the top and a scoop of vanilla, 2 vanillas? And so it starts to get a little bit complicated. If you care about investigating that other concept, the other idea of mixing flavors, that's going to actually lead us to a much larger answer. We're not going to consider that here, but if you want to talk about it, let's talk about it in class. I look forward to it because it's really an interesting discussion. However, for simplicity's sake, we are going to look at this as the fact that we've got 1, 2, or 3. So those are 3 choices in sizes. And then we're going to look at it as, I'm going to put size here. Or amount I could have put. We're going to have 3 choices in sizes, 1, 2, or 3 scoops. The next thing we have is 12 different flavors, and I'm going to assume that we're just choosing one flavor for our ice cream. So we've got 12 different flavors, and I'll put flavors here. All right, and then it can be served on a waffle cone, sugar cone, or in a cup. So that's 3 different choices for servings. Okay, all right. So then when I multiply 3 times 12 times 3 again, I'm going to get 108. So there's 108 different ways you can be served ice cream at this particular ice cream shop that has these things. Make sense? All right, this video went a little bit longer than I expected, so I'm going to let you guys go. I hope this makes sense. You don't have to copy the notes, but you do have to understand them. I'll talk to you guys soon. Bye-bye.